temperature, perception, and the first limits of reality. Every living organism, from microscopic bacteria to complex multicellular life, is capable of sensing heat and cold. This ability is ancient. It appeared long before intelligence, technology, or language. But what we feel is not temperature itself. T is the flow of heat. When you touch a cold surface, your skin is not measuring numbers. It is simply losing energy. The faster energy leaves your body, the colder something feels, even if, in reality, two objects have the same temperature. This is why metal feels colder than wood in the same room. Not because it is colder, but because it steals heat faster. Human senses were never meant to measure reality precisely. They evolved only to keep us alive, and that is where instruments enter the story. To understand temperature objectively, humanity had to abandon sensation and trust devices. Thermometers do not feel. They respond. They expand, contract, emit radiation, change electrical resistance, all in predictable ways. This measurable behavior is what we call empirical temperature. T is temperature defined by procedure, not perception. At first, people needed reference points. Ice melting, water boiling. Between those points, scales were divided into equal steps. This is how Celsius and Fahrenheit were born, practical, human-friendly systems designed for daily life. But nature does not recognize ice or boiling water as fundamental boundaries. Those scales are conveniences, not truths. If we want a temperature scale that belongs to the universe itself, we must go deeper. We arrive at absolute temperature, measured in kelvins. Kelvin does not begin at freezing water. It begins at something far more profound, absolute zero. The lowest possible temperature that matter can reach. At this point, thermal motion reaches its minimum limit. Particles cannot slow down any further without violating the laws of physics as we understand them. You can approach absolute zero, but you never truly cross it. It is not a line you step over. It is a cliff at the bottom of reality, and if there is a bottom, there must also be a top. Or so it seems. For decades, physicists asked the same quiet question: how hot can anything possibly become? On Earth, the hottest temperatures ever created did not come from fire, lava, or explosions. They came from machines, particle accelerators. Inside them, heavy atomic nuclei are pushed to velocities unimaginably close to the speed of light. When these ions collide, their energy compresses into a region smaller than an atom. For a fraction of a second, matter stops behaving like matter. Protons and neutrons melt. Atomic nuclei dissolve. Even their internal structure breaks apart. What forms is a quark gluon plasma, a state of matter that existed moments after the birth of the universe. Temperatures reach trillions of degrees, numbers so large they lose emotional meaning, and yet, even this is not the final limit. These temperatures exist only briefly, only in tiny regions, only because our technology allows it. For now, so the question remains open: if Earth can do this, what does the universe itself create? And to find out, we must leave our planet behind. We begin our journey close to home, with a world that looks familiar in size, but hostile in every other way. Venus. A planet wrapped in an atmosphere so dense that it crushes and cooks simultaneously. Pressure equal to 90 Earth atmospheres. Heat trapped relentlessly by carbon dioxide clouds. The surface temperature remains almost constant, day and night, hot enough to melt lead. Venus is not warmed by the sun alone. It is imprisoned by its own air. A reminder that similarity in size does not mean similarity in fate, moving outward. We encounter objects that flirt dangerously close to the sun. Some asteroids dive inward on extreme orbits, briefly becoming blazing stones during their closest approach. But one of the greatest thermal surprises in our solar system is not a planet, and not an asteroid. It is a moon.io, orbiting Jupiter. A world torn from the inside by gravity itself. Jupiter's immense tidal forces need Io continuously, generating internal heat that fuels thousands of volcanoes. Some of them burn hotter than any lava on Earth. Io is heated not by sunlight, but by gravity. A reminder that heat can come from motion, pressure, and distortion, not just fire. And then, of course, there is the sun. Its visible surface burns at about 5,500 degrees Celsius, already far beyond anything natural on Earth. But above that surface lies a mystery. The solar corona. A vast, ghostly halo extending millions of kilometers into space. There, temperatures soar into the millions of degrees. Hotter than the surface below it. An apparent paradox explained only by magnetic fields, plasma waves, and violent energy release on invisible scales. Sometimes, this energy is unleashed suddenly, in solar flares and eruptions, where temperatures spike even higher. Yet despite all this power, the Sun is an ordinary star, average, unremarkable, one among hundreds of billions, and the universe has built far hotter furnaces than this. As we move deeper into space, temperature begins to lose its everyday meaning. It stops being about warmth and starts becoming a story about energy itself, and that story is only just beginning. Stars that burn beyond blue, and the quiet edge where physics begins to fade when we look at stars. Color seems simple: red, yellow, white, blue, but color is not decoration. It is temperature made visible. The cooler a star is, the redder it appears. As temperature rises, color shifts toward white, and then toward blue. Blue does not mean calm. Blue means violence. It means energy so intense that most radiation escapes in invisible wavelengths. Ultraviolet and beyond. What we see is only the faint edge of something far more extreme. Most stars fall within a familiar range, but the universe does not stop there. It always builds exceptions, and among the most dangerous and short-lived of these exceptions are stars known as Wolf-Rayet stars. These are massive stars in the final stages of their evolution. They are not stable suns quietly shining for billions of years. They are exposed cores, their outer layers have been stripped away by ferocious stellar winds, revealing inner regions normally hidden deep inside a star. As a result, their surface temperatures soar far beyond those of ordinary stars, tens of thousands, sometimes over 100,000 kelvins, and they lose mass at astonishing rates, throwing matter into space faster than any calm system can sustain. One of the most extreme known examples is a star called WR102. Its surface temperature is estimated at more than 200,000 kelvins. This is not a typo. 200,000. For comparison, the surface of our Sun is just under 6,000 kelvins. WR102 radiates so intensely that its visible light is almost irrelevant. Most of its energy pours out in ultraviolet radiation capable of sterilizing entire regions of space. And yet, even this is not the hottest thing a star can become, because stars do not always end quietly. When a star like our Sun dies, it sheds its outer layers and leaves behind a dense core. A white dwarf. These stellar remnants no longer produce energy through nuclear fusion. They simply cool, slowly, over billions of years. At least, that is the general rule, but some white dwarfs are caught extremely early in this cooling process, and in that moment, they can be unimaginably hot. The hottest white dwarf ever observed, RxJ0439, has a surface temperature of roughly 250,000 kelvins. A dead star, already past its prime, still hotter than nearly every living star in the galaxy. White dwarfs remind us that death in the cosmos is not always cold. Sometimes it is blindingly hot. Then there are objects where temperature stops being just a surface property. Neutron stars. These are the collapsed cores of massive stars that exploded as supernovae. They pack more mass than the Sun into a sphere only a few tens of kilometers across. Gravity becomes so intense that atomic structure collapses. Electrons merge with protons. Matter turns into neutrons. When a neutron star is born, its temperature can reach hundreds of billions of degrees. In those first moments, it radiates intensely in X-rays and gamma rays. Over time, it cools, but even after millions of years, neutron stars remain extraordinarily hot compared to ordinary objects. Here, temperature is no longer just heat. It is a symptom of pressure, collapse, and extreme density. And then, we arrive at the edge, the point where our everyday language begins to fail. Black holes. A black hole itself does not have a surface temperature in the normal sense. There is no surface, no solid boundary, only an event horizon, a one-way limit in spacetime. But the matter falling toward a black hole tells a different story as gas spirals inward. It accelerates, compresses, and heats up the centers of active galaxies. This process creates quasars, the brightest persistent objects in the universe. The inner regions of these accretion disks reach temperatures so high that physicists describe them using something called effective temperature, a way to translate radiation intensity into thermal language. In the quasar 3C273, estimates suggest effective temperatures of tens of trillions of degrees in its central regions, numbers so extreme they begin to lose physical intuition. At this point, temperature becomes less like heat and more like energy density. And here we must pause, because something subtle happens. Temperature, as a concept, is defined precisely only for systems in thermal equilibrium, that is, systems where particle energies follow stable statistical distributions. But many of the hottest places in the universe are not calm or stable. They are chaotic, explosive, rapidly changing. Calling these states hot is useful, but not exact. This is where theory introduces an idea known as the Planck temperature. A scale so high that our current physical theories, quantum mechanics, and general relativity can no longer operate independently. At or above this level, spacetime itself may behave differently, not because the universe forbids higher temperatures, but because our understanding breaks down. And there is another twist. As temperature increases, matter does not simply get hotter. It changes form. Molecules break apart into atoms. Atoms lose electrons. Nuclei dissolve into protons and neutrons. Protons and neutrons melt into quarks. At each step, reality simplifies and becomes harder to describe. Eventually, we reach a point where even quarks, fundamental particles, have nothing left to break into. What happens beyond that? We do not know, and perhaps that is the most honest answer physics can give. There may be no absolute maximum temperature, only limits to our ability to describe what comes next. Yet despite these abstract extremes, there exist stars we can actually see with our own eyes. Stars that quietly hold records, stars whose heat is not theoretical but visible, and among them shines one particularly remarkable object in the southern sky. A star called Neos, and its story is not about theory, but about destiny. Neos, the hottest star you can see, and the silent countdown of massive suns. If you look into the night sky, most stars appear calm, small points of light, distant, unchanging. They seem eternal, but this is an illusion. Stars are not static objects. They are processes, and the most massive among them live fast and die violently. In the southern sky, in a constellation once imagined as part of a colossal celestial ship, shines a star with a simple, ancient name, Neos. Its formal designation is Zeta Puppis, but its common name comes from Greek, meaning ship. A fitting name for a star that once belonged to an enormous constellation, later broken apart because it was simply too large to manage on the sky. Even its cartography hints at excess. Neos is not just another bright point. It is a blue supergiant. A massive star in a short and dangerous phase of its existence. Stars like this are born with tens of times the mass of our Sun. That mass means pressure. Pressure means faster nuclear reactions. And faster reactions mean a much shorter life, where the Sun will shine calmly for 10 billion years. A blue supergiant may live only a few million. In cosmic terms, a brief flash. At this stage, something counterintuitive happens. Nuclear fuel in the core becomes harder to fuse. The balance inside the star shifts. The star may contract. Its surface area decreases. Energy becomes concentrated. The surface temperature rises dramatically. This is how a red supergiant can transform back into a blue one. Neos is believed to be in such a phase, compressed, heated, and shedding mass through an intense stellar wind. A wind moving at thousands of kilometers per second, not a breeze. A constant outflow of matter powerful enough to reshape the surrounding space. The surface temperature of Neos is estimated at around 40,000 kelvins. This makes it one of the hottest stars visible to the naked eye from Earth. For comparison, the Sun's surface temperature is under 6,000 kelvins. The difference is not subtle. Most of Neos's radiation does not shine invisible light at all. It pours into ultraviolet. If that energy was shifted into the visible spectrum, Neos would dominate the sky far more dramatically than it does now. Its true power is mostly invisible, and that is often how danger works in the universe. Neos is also remarkable for another reason. It is moving fast, much faster than most nearby stars. Astronomers classify it as a runaway star, an object traveling through space with an unusually high velocity relative to its surroundings. Runaway stars do not accelerate themselves without reason. They are often survivors. The most likely explanation is a violent past. Neos may once have been part of a binary system, two massive stars orbiting one another. When one of them exploded as a supernova, the balance was destroyed. The remaining star, Neos, was flung outward, carrying the memory of that explosion in its speed. A silent witness to an ancient catastrophe, still burning, still moving, still counting down. Massive stars do not fade quietly. Neos continues to burn through its fuel. It will lose mass relentlessly. Stellar winds will strip away its outer layers, exposing deeper regions. Over time, its temperature and size will change again. Eventually, fusion in the core will reach iron, the element that ends the energy-producing chain. At that moment, the star's fate is sealed. Gravity will win. The core will collapse in a fraction of a second. The outer layers will rebound outward in a titanic explosion. A supernova, for a brief time, Neos will outshine entire galaxies. If this happened close enough, it could be visible even during the day from Earth. Such an event would be breathtaking and potentially dangerous, depending on distance and orientation. What remains afterward is uncertain. The core could compress into a neutron star or collapse further, becoming a black hole. Both outcomes are possible for stars of this mass, but either way, Neos will not simply disappear. It will transform. And the energy released in its death will seed space with heavy elements, the raw materials for future stars, planets, and life. There is something deeply humbling in this. Every atom heavier than hydrogen in your body was forged in stars like Neos. Carbon, oxygen, iron, calcium, all were created in stellar furnaces and scattered by explosions. The heat that makes Neos dangerous is the same heat that made existence possible, and yet, despite its power, Neos is just one example. A single star among countless others, each following its own path toward collapse, transformation, or quiet fading. The night sky looks peaceful because timescales are enormous, but behind that calm lies constant change, birth, burning, explosion, silence over and over again. And while stars like Neos represent the upper extremes of visible heat, they are not the only places where temperature reshapes reality closer to us. On worlds that orbit stars rather than becoming them, heat tells very different stories. Stories of planets that rotate too slowly, worlds with crushing atmospheres, skies where metal rains from clouds, and that is where our journey goes next. Venus, locked worlds, and the planets where heat rewrites reality. When people think about hostile planets, they often imagine distant exoplanets far beyond our solar system, worlds of fire and storms, orbiting alien stars. But one of the most extreme examples of runaway heat is much closer. So close that we once believed it might be similar to Earth. Venus. At first glance, Venus seems almost familiar, nearly the same size as Earth, a rocky planet located in the inner solar system. But this similarity is deceptive. Venus is wrapped in an atmosphere so dense that it transforms sunlight into a permanent prison of heat. The pressure at its surface is more than 90 times that of Earth. The temperature remains nearly constant, day and night, hot enough to melt lead, not because Venus is closer to the Sun than Mercury, but because its atmosphere refuses to let heat escape. This is the runaway greenhouse effect in its purest form. A reminder that climate is not just about distance, but about balance. For decades, Venus remained difficult to study. Its thick clouds hide the surface completely. Visible light tells us almost nothing, but in recent years, a single spacecraft has been quietly rewriting what we know. The Japanese probe Akatsuki orbiting Venus since 2015. It has revealed a planet that is far from static. Venus's atmosphere is alive, layered, dynamic, restless. Point 1. Of its strangest features is something called superrotation. The atmosphere of Venus moves faster than the planet itself, while the solid planet rotates extremely slowly. 1 Venusian day lasts longer than a Venusian year. The upper atmosphere circles the planet in just a few Earth days. Winds reach hundreds of kilometers per hour. The sky races while the ground barely turns. This phenomenon is not just a curiosity. It may be a key to understanding many distant worlds, because Venus is not unique in rotating slowly. In fact, slow rotation may be common among exoplanets, especially those that orbit close to their stars. Such planets often become tidally locked, always showing the same face to their star. Point 1 Hemisphere trapped in eternal daylight, the other frozen in endless night. Without an atmosphere capable of transporting heat, such worlds would tear themselves apart climatically. The day side would overheat. The night side would collapse into deep freeze. But if superrotation develops, heat can be redistributed, and the planet survives. In this way, Venus becomes a natural laboratory for worlds light years away. And yet, Venus also reminds us of something darker. Small changes can trigger irreversible outcomes. A slight increase in greenhouse gases, a small shift in rotation, a different early history, and a potentially habitable world becomes uninhabitable forever. From Venus, let us look outward again, this time not at heat, but at alignment. A T-shadows cast across worlds. Eclipses. On Earth, eclipses feel special, rare, precise, almost magical. But in reality, an eclipse is geometry. You need 3 things: a star, a planet, and an object large enough to block the light. Mercury and Venus have no moons, so no true solar eclipses occur there. Mars has moons, but they are too small to fully cover the sun. They create brief, partial eclipses, more like flickers than darkness. Gas giants, however, are surrounded by massive moons from the right vantage point. Those moons can completely eclipse the distant sun, though there is a catch. Gas giants have no solid surface to stand on. An eclipse there would be witnessed from a floating platform, or a spacecraft suspended in the upper atmosphere. Still, the geometry works, and beyond the solar system, eclipses become tools rather than spectacles. Exoplanets are often discovered because they eclipse their stars. As a planet passes in front of its star, the star's brightness dips ever so slightly. That tiny change, sometimes less than 1%, reveals the planet's presence, and more than that, as starlight passes through the planet's atmosphere, it carries chemical fingerprints. This is how we learned that some planets are losing their atmospheres entirely. Point 1 of the first and most famous examples is the planet, often nicknamed Osiris. A gas giant orbiting so close to its star that its atmosphere is stretched and heated until it escapes into space. Hydrogen streams away, forming a vast, invisible tail. A planet slowly evaporating. Heat, once again, rewriting destiny. But Osiris is only the beginning. As observations improved, astronomers began to find worlds even closer to their stars, planets with orbital periods measured in hours, not days. Worlds where the day side reaches temperatures normally associated with small stars. These are the ultra-hot Jupiters, gas giants locked in place, their atmospheres flowing like rivers of fire from day side to night side. In these worlds, chemistry breaks down, molecules tear apart, atoms ionize, metals vaporize, weather becomes something else entirely, and among these alien worlds are planets that look beautiful until you understand them. Point 1 such world appears deep blue from space, not because of oceans, not because of sky, but because its atmosphere contains tiny particles of silicates, the same materials that form glass on Earth under extreme heat. These particles melt and condense into droplets. The planet's upper atmosphere scatters blue light, turning it into a sapphire-colored sphere, but inside that beauty are winds moving at several kilometers per second, carrying molten glass sideways through the sky. A storm of razor-sharp rain on other worlds. Iron itself may condense and fall on the night side, metal clouds. Metal rain. Heat creates skies that belong more to furnaces than to planets. These are not worlds of life. They are worlds of process, places where physics operates without compromise, and yet, even these hellish planets matter because they teach us contrast. They show us what happens when energy overwhelms structure. They help define the narrow window in which stability and life can exist. Every extreme world sharpens our understanding of Earth.so as our journey continues. We begin to see a pattern. Heat is not just a number. It is a force that decides whether matter builds or dissolves, whether atmospheres remain or escape, whether planets stabilize or tear themselves apart. And still, we have not reached the most haunting examples. There are worlds where planets orbit dead stars, where gravity crushes light itself, where time slows and temperature becomes secondary to something even more absolute. That is where our path leads next. Beyond the hottest fires, when temperature stops being a number. Up to this point, we have treated temperature as something measurable: degrees, scales, limits. But now we must step into a region where temperature begins to lose its familiar meaning. In classical physics, temperature is simple. T is the average kinetic energy of particles in a system. Faster motion, higher temperature. Slower motion, lower temperature. This idea works beautifully for gases, liquids, solids, and even for plasma. As long as the system is calm enough, as long as it is close to equilibrium. But the universe is not always calm. Extreme energies. Systems stop behaving statistically. Particles no longer form neat distributions. They are created and destroyed too quickly. They collide, decay, and transform before equilibrium can even form. In such conditions, asking for the temperature is like asking for the average shape of an explosion. You can describe parts of it, but not the whole. This is why, at the highest extremes, physicists speak carefully. They introduce terms like effective temperature or energy density, not because temperature disappears, but because it becomes an approximation. A translation, a metaphor. And yet, there is one moment in cosmic history where temperature dominates everything. A moment so early that time itself barely exists in a familiar sense. The beginning, according to modern cosmology. The universe began in a state of extreme density and energy, not an explosion in space, but an expansion of space itself. Everywhere at once. No center, no edge. That earliest moment, the temperature of the universe was unimaginably high. So high that matter as we know it could not exist. No atoms, no nuclei, no particles with mass in the usual sense, only pure energy and quantum fields. Yes, the universe expanded. It cooled, not because heat escaped anywhere, there was nowhere to escape to, but because expansion spreads energy out. Cooling was inevitable, and cooling changed everything. Specific temperatures. New forms of reality emerged. First, fundamental forces separated from one another. Then, particles gained mass. Later, quarks combined into protons and neutrons. Minutes later, the first atomic nuclei formed. Hundreds of thousands of years later, atoms appeared. Only then could light travel freely. Only then did the universe become transparent. This slow descent through temperature is what shaped everything we see today. Galaxies, stars, planets, life. Heat was not just destruction. It was structure waiting to happen, and somewhere near the very beginning, the temperature approached what physicists call the Planck temperature. This is not just a large number. It marks a boundary between what we understand and what we do not. At the scale, space and time themselves are expected to fluctuate violently. Distances lose meaning. Moments blur together. Gravity becomes quantum. Quantum mechanics becomes geometric. Our equations stop giving answers, not because reality ends, but because our language does. It is important to understand this. The Planck temperature is not proven to be the maximum. Temperature.it is the maximum describable temperature. Within our current theories, beyond it, we are blind, and there is something deeply humbling in that we can measure temperatures inside stars. We can recreate conditions from the early universe inside particle accelerators. We can simulate exotic matter with supercomputers. But there exists a regime where knowledge itself becomes the limiting factor, not energy, not matter. Understanding. So when we ask, is there a highest temperature? The honest answer is this: we do not know, and anyone who claims certainty is not being careful enough. The universe may allow temperatures far beyond anything we can imagine. Or it may impose limits through mechanisms we have not yet discovered. Either way, we stand at the edge of comprehension, looking inward toward equations that no longer work, and outward toward a past we cannot directly observe, and still, this ignorance is not failure. It is an invitation. Every boundary in physics has eventually become a doorway, and beyond this doorway lie questions even stranger than heat. Questions about time, about space, about whether reality itself has a smallest scale or a highest intensity. But those answers belong to another chapter. For now, we remain suspended in this quiet uncertainty between the hottest fires imaginable and the silence that follows understanding, and the journey is far from over. When matter forgets its shape, temperature as transformation. So far, we have spoken about temperature as a scale. As something that rises, something that breaks records, but temperature is not only a number. It is a process. It changes matter step by step, quietly at first, then violently. At low temperatures, matter is orderly. Atoms bind into molecules. Molecules arrange into crystals. Structures form and persist. Cold favor stability. It allows patterns to exist for a long time, but as temperature rises, order begins to loosen. First, molecules vibrate, then their bonds weaken. Eventually, they break apart. A solid becomes liquid. A liquid becomes gas. At this stage, matter is still familiar, chaotic, but recognizable. Atoms remain intact. Increase the temperature further, and atoms themselves cannot survive. Electrons are torn away from atomic nuclei. What remains is plasma, a state of matter so common in the universe that stars themselves are made of it. Plasma. Electric and magnetic forces dominate. Matter glows, conducts, responds to fields. This is the realm of stars, nebulae, and lightning. But even plasma has limits. Raise the temperature again, and nuclei begin to fall apart. Protons and neutrons can no longer remain bound. Nuclear matter melts. This does not happen in ordinary stars. It requires energies found only in supernovae, neutron star collisions, or particle accelerators. Here, matter enters a more primitive phase. Beyond this point, protons and neutrons themselves lose their identity. They dissolve into their fundamental components, quarks, gluons. This is the quark-gluon plasma. A state that filled the universe microseconds after its birth. A state where matter is no longer built. It is only available, nothing solid, nothing stable, just energy and potential. In this regime, temperature no longer describes comfort or danger. It describes permission. What reactions are allowed? What structures are forbidden? At higher temperatures, the universe forbids complexity. At lower temperatures, it allows it to return. This is a profound idea. Structure is not guaranteed. It is negotiated with temperature. Life itself is a temporary agreement between energy and order, and still, even quark-gluon plasma may not be the final step, because quarks are considered elementary particles. They cannot be broken down into smaller constituents. At least, not according to current knowledge. So what happens if temperature continues to rise? We do not know. Our equations stop there. We reach a conceptual wall. Beyond it, we can only speculate. Some theories suggest that at extreme energies, forces unify. Electromagnetism, weak force, strong force, becoming one. In such a state, the distinctions we rely on cease to exist. Particles may lose identity. Symmetries may dominate. Reality becomes simpler, but also stranger. And here, temperature becomes something else. Again, not a measure of motion, but a measure of possibility. What kinds of reality can exist at all? This reframes the original. Question: what is the highest temperature? Is not only a question about heat, it is a question about how much simplicity the universe can tolerate, how much structure it can temporarily erase before rebuilding everything. Again, because cooling is not destruction, cooling is creation. As temperature falls, the universe does not lose complexity. It gains it. Particles combine, forces separate, matter organizes, stars ignite, planets form, chemistry begins, eventually, biology, all because temperature dropped below critical thresholds. So when we explore extreme heat, we are not just chasing records. We are studying the reset button of reality, the conditions under which everything becomes possible again, but nothing can last. And as we continue forward, we must ask a different kind of question, not how hot can it get, but what happens when temperature stops being the main actor? Because beyond heat, other limits begin to dominate: limits of gravity, limits of space-time, limits of observation itself. And that is where our journey leads next. Heat without light. Does darkness have a temperature? Until now, heat was always tied to matter. To particles, to motion, to collisions. Something had to move for temperature to exist. But the universe contains far more than visible matter. Most of it is invisible, silent, dark. Astronomers discovered this absence not by seeing something new, but by noticing that something was missing. Galaxies rotated too fast, clusters held together too strongly. Gravity was stronger than visible matter could explain. Something unseen was shaping the cosmos. We call it dark matter. Dark matter does not shine. It does not emit light. It does not absorb light. It passes through ordinary matter almost without interaction, and yet it has mass, which raises a strange question. Can something invisible have a temperature? Or is temperature meaningless in the dark? In physics, temperature requires interaction. Particles must collide, exchange energy, reach some form of balance. Dark matter barely interacts with itself or with normal matter. It does not collide often. It does not glow. It does not radiate away energy. So if dark matter has a temperature, it must be defined very differently. Cosmologists speak of cold and hot dark matter, but these words do not mean warm or freezing in the everyday sense. They describe speed. Cold dark matter moves slowly compared to the speed of light. Hot dark matter moves fast. This difference matters enormously because speed determines how structure forms. Slow-moving matter clumps easily. Fast-moving matter smooths everything out. If dark matter were hot, galaxies might never have formed. Structures would dissolve before they could grow. The universe would remain featureless and thin. But dark matter appears to be cold, slow enough to gather, dense enough to seed galaxies. In this way, the temperature of something unseen shaped everything we see, and yet dark matter remains thermally isolated. It does not cool like stars. It does not heat like gas. It simply exists, persistent, unchanging, detached from thermal drama. In a universe defined by fire and cooling, dark matter is strangely indifferent. This introduces a quiet shift in our understanding. Temperature is not universal. It does not apply equally to everything that exists. Some parts of reality play by different rules. And now, we must go further, beyond dark matter, beyond particles, beyond even temperature itself, because there are regions of the universe where heat becomes irrelevant, not because it is too small, but because something else dominates. Gravity. Imagine falling toward a black hole. Far away, nothing seems unusual. Time flows normally. Temperature behaves as expected, but as you approach the event horizon, everything changes, not instantly, not violently, quietly, subtly. From the outside, you appear to slow down. Your clocks tick more slowly. Your motion stretches. Heat still exists, but time itself begins to distort. Temperature depends on time. On motion per unit time. If time slows, so does the meaning of heat. Near extreme gravity, energy behaves differently. Radiation redshifts. Particles lose apparent energy. What was once hot appears cooler to a distant observer, not because energy vanished, But because time changed, this leads to a strange realization: temperature is not absolute. It depends on perspective, on gravity, on motion, on space-time itself. Point 2: observers can disagree about how hot something is, and both be correct. Even empty space is not truly cold. Quantum theory tells us that vacuum itself contains fluctuations, virtual particles appearing and vanishing. A background hum that never fully stops. The larger scales. This emptiness has a temperature too. The cosmic background. A faint afterglow from the early universe, just a few degrees above absolute zero. Cold, but not zero. Never zero. So now we see a broader picture. Temperature is not just heat. It is interaction, motion, perspective. In some regions of the cosmos, temperature defines reality. In others, it fades into irrelevance, and beyond that, new limits appear. Limits not of heat, but of knowledge. Of observation. Of what can ever be measured, and that is where the silence becomes deeper still, because the next boundary is not physical. It is observational. A horizon no temperature can cross, and that is where we go next. The horizon of heat, temperatures. No one can ever measure. There is a moment when curiosity reaches a wall, not because the universe ends, but because information does. This wall is not made of matter, not of energy, not even of temperature. It is made of distance and time. Everywhere you look in the sky, you are looking into the past. Light takes time to travel from the sun, minutes. From nearby stars, years. From distant galaxies, billions of years. The farther you look, the older the light becomes eventually. You reach a limit. A boundary beyond which no signal has had time to reach us. This boundary is called the cosmic horizon. Beyond this horizon, space still exists, galaxies still form, stars still burn, temperatures still rise and fall. But none of it can ever be observed by no light. No particles, no information, forever unreachable. This has a strange consequence. There may exist regions of the universe hotter than anything we know, colder than anything we can imagine, more extreme than all our theories combined, and we will never know, not because technology is insufficient, but because physics forbids the information from arriving, even within the observable universe. Horizons exist. Black holes create their own horizons. Event horizons cross one, and information is cut off. Temperature inside may be defined, or it may not from the outside. It becomes irrelevant. Nothing that happens there can affect us. Again, heat without consequence. And then there is the most subtle horizon of all, the particle horizon. Of the early universe. In its first moments, the universe expanded so rapidly that regions lost causal contact. They could not exchange heat, could not reach equilibrium, and yet they now appear nearly the same temperature. This mystery puzzled physicists for decades. How could distant regions that never touched share the same thermal history? The answer lies in inflation, a rapid expansion that smoothed the universe before separation occurred. But even inflation has limits. It does not remove all horizons. It merely rearranges them. So temperature, once again, depends on connection. On interaction, on shared history. Where interaction ends, temperature becomes unknowable, not undefined, but unmeasurable. This is a critical distinction. The universe does not owe us access to its extremes. Reality exists independently of observation. We can only describe what can influence us. Everything else remains silent, and silence is not emptiness. It is fullness without language, without numbers, without degrees. Imagine a region beyond our horizon where stars burn 10 times hotter than anything in our sky. Or a region so cold that matter barely moves at all. These states may exist right now, but without connection. They might as well be myths, real, but unreachable. This changes how we think about limits. There may be no maximum temperature in the universe as a whole, only maximum temperatures within regions that can interact, local limits, not global ones. The universe may contain every possible extreme, each isolated by distance and time, and so When we ask about the hottest place that exists, we must add a quiet clause that exists for us, for observers inside this horizon, bound by this light cone, trapped inside this slice of spacetime, beyond that. Questions lose meaning not because they are wrong, but because they cannot be answered, and yet we keep asking, because pushing against these limits reveals something deeper, not about heat, but about ourselves, about what it means to know, and what it means to accept uncertainty as we continue forward. We must now confront the most unsettling idea yet, that the limits we encounter are not imposed by the universe alone, but by the structure of observation itself, and that, more than any extreme temperature, may be the coldest truth of all. The observer's fire. Why temperature depends on who is watching up to this point. We have treated temperature as something that exists on its own, a property of matter, a number written into reality, but now we must introduce someone else into the equation. The observer. In everyday life, we assume temperature is absolute. Water boils at a fixed value. Ice melts at another point. Two people standing in the same room agree on what is hot and what is cold. This works because we live at low speeds, weak gravity, and shared conditions. The universe, however, does not always offer such comfort. According to relativity, time itself depends on motion and gravity. Move fast enough, and your clock slows down. Fall deep enough into gravity, and time stretches. And since temperature is tied to motion per unit time, temperature, too, becomes relative. This is not philosophical speculation. It is mathematics. Point 2. Observers, moving differently, can disagree about the temperature of the same system, and both can be correct. Imagine a box filled with radiation. One observer. The particles inside have a certain energy distribution. Another observer. Moving at high speed, those same particles appear blue-shifted, higher energy, higher temperature. Nothing inside the box changed, only the observer did. This means something unsettling. Temperature is not just a property of matter. It is a relationship between matter and the observer's frame of reference. Heat is not only there. It is there for someone. Gravity deepens this effect. Near a massive object, time slows. Processes unfold differently. From far away, radiation climbing out of gravity loses energy. It appears cooler. An observer close by. Nothing changed. A distant observer. Everything cooled. Same photons. Different clocks, different temperatures. And then there is the most extreme case, acceleration itself. An observer accelerating through empty space detects something extraordinary. A warm glow even when space is otherwise cold. This is known as the Unruh effect. An accelerating observer perceives a thermal bath where an inertial observer sees vacuum. Temperature without heat source. Heat without matter created purely by motion. This tells us something profound. Temperature is not fundamental in the way we once thought. It emerges from perspective, from interaction between observer, motion, and spacetime. Without an observer, temperature has no meaning at all. Only energy distributions exist. This shifts the question again. What is the highest temperature? Cannot be asked without asking for whom? Measured where? Measured how? Measured in which frame? The universe does not carry a single thermometer. It carries infinitely many, each attached to a different path through spacetime, each telling a slightly different story. This does not make physics weaker. It makes it more honest. It admits that reality is richer than any single viewpoint, that extremes are contextual, that even heat is not immune to relativity. And now, having crossed this threshold, we must face a final shift in thinking. Because if temperature depends on observers, then what happens when observation itself breaks down? When there is no observer that can exist under such conditions? At what point does temperature lose meaning, not because it is too high, but because nothing can remain to experience it? That question takes us beyond physics alone, into the limits of existence itself, and that is where our journey continues. The limits of survival, when heat erases the observer itself. Until now, we have spoken about temperature as something that can always be measured. As long as there is an observer, as long as there is a frame of reference. as long as something exists to ask the question. But now we must confront a far more uncomfortable idea. What if temperature reaches a point where no observer can exist at all? Not because instruments fail, but because existence itself fails. Every form of observation requires structure, and an observer must have boundaries. Internal states, memory, time to compare one moment to another. Even the simplest detector must remain intact long enough to register change. Temperature threatens this requirement, because heat is not merely energy. It is disruption. At low temperatures, matter is stable, atoms hold electrons, molecules persist, crystals retain shape, information can be stored. Life is possible because structures last, but as temperature increases, stability becomes temporary, vibrations grow stronger, bonds weaken, patterns dissolve, order becomes fragile. At a few hundred degrees, organic molecules begin to fail, proteins unravel, DNA breaks apart, life ends quickly, but observation does not. Machines still function. Sensors still respond. The observer survives long after biology is gone. Raise the temperature further, metals soften. Semiconductors lose function. Circuits short and melt. At thousands of degrees, no conventional machine can survive, but atoms still exist. Observation becomes harder, but not impossible in principle. Now we cross a deeper threshold. T tens of thousands of degrees. Atoms cannot remain intact, electrons are stripped away, matter becomes plasma. Here, information storage becomes difficult. No fixed structures, no stable bonds. Still, plasma can be studied, stars are plasma, and we observe them constantly. The observer remains outside, safe, cool, distant. But imagine being inside such conditions, not observing from afar, but embedded within. At some temperature, no material object can remain coherent long enough to act as an observer. Not biological, not mechanical, not hypothetical, because the very components that would perform observation are torn apart faster than they can interact meaningfully. This introduces a radical boundary. A survivability limit, not of life, not of technology. Of existence as a structured process. Beyond this point, temperature does not merely kill observers. It prevents them from ever forming. This is not science fiction. It is a logical consequence of how matter behaves. To observe something must persist through time. Temperature is motion. At extreme levels, motion becomes too violent for persistence. No clocks, no memories, no states, only flux. Now consider this carefully. If no observer can exist above a certain temperature, then temperature beyond that point cannot be measured, not even in principle, because measurement is an act that requires survival. This creates an absolute epistemic limit, not a limit of instruments, not a limit of theory. A limit of being. Beyond this boundary, reality may still exist, but it cannot be experienced, recorded, or known from within. This forces us to reframe the question yet again. The question is no longer, what is the maximum temperature? But instead, what is the maximum temperature at which an observer can exist? And this is a much lower number, not trillions. Not Planck scale, much lower, because observers require structure, and structure requires stability. This may explain why the universe cooled so quickly after its birth, not just to allow atoms, but to allow observation itself. A universe that never cooled would be a universe without witnesses. No memory, no history, no experience, just eternal, unrecorded flux. And here we arrive at a subtle but profound realization. The fact that we can ask these questions already constrains the universe. It tells us that we exist below certain thermal thresholds. Our very presence is evidence of cosmic cooling. This does not make us special. It makes us conditional. We are permitted by temperature, allowed by physics to exist at all. And so, when we imagine regions of extreme heat, early cosmological epochs, colliding neutron stars, singularities, we must accept something humbling. There may be realms where reality happens without witnesses, where temperature is real, but unknowable, not because it is hidden, but because nothing can remain long enough to notice it. And yet, this is not the end of the story, because even if observers cannot exist inside such extremes, They may still exist outside them, watching boundaries, measuring consequences, inferring what cannot be entered. The universe often hides its deepest truths behind walls that cannot be crossed, but it leaves fingerprints, and those fingerprints are where we go next. The boundary of knowability, when reality exists without witnesses at this stage of the journey. We must slow down even further, because we are no longer discussing how hot something can be. We are discussing whether it can ever be known. Physics often assumes that reality exists independently of observation. Stars burn whether we look at them or not. Galaxies collide without asking permission, but knowledge is different. Knowledge requires interaction. Something must happen that leaves a trace. A signal, a particle, a distortion in space-time. Without a trace, there is no measurement. And without measurement, there is no description. Extreme temperature challenges this deeply, not because heat destroys objects, we already know it does, but because heat can erase the very possibility of interaction. Imagine a region of space so hot that particles exist only briefly. They are created and destroyed faster than they can exchange information. No stable states, no repeatable processes. No correlations that persist. In such a region, nothing can act as a messenger. Not light, not matter, not even fields in any classical sense. From the outside, we may infer that such a region exists from its gravitational effects, from its influence on surrounding matter. But the interior itself is sealed, not by walls, but by impermanence. This leads us to a strange conclusion. There may exist regions of reality that are ontologically real but epistemically inaccessible. They exist, but cannot be known, not because of distance, not because of time delay, but because no information survives long enough to escape. This is different from a black hole horizon. A black hole hides information behind geometry. Extreme temperature hides information behind instability. Both lead to silence, but for very different reasons. This distinction matters because it tells us that not all unknowable things are unknowable in the same way. Some are hidden by space, some by time, some by heat, and some by combinations we barely understand. Now consider the early universe again. In its first instance, the temperature was so high that familiar particles did not exist. Forces were unified. Mass had no meaning. Time itself was poorly defined. If an observer had somehow existed then, what would they observe? The answer may be nothing coherent. No structures, no events that persist, no before and after. In any recognizable sense, the universe was not only hot. It was unrecordable. Cooling did more than allow matter to form. It allowed history to begin. Only when temperature dropped below certain thresholds could processes leave lasting traces. Only then could cause follow effect in a way that could be remembered. In this sense, temperature governs the existence of the past. This is a radical idea, that there may be phases of the universe that did not merely precede memory, but could never be remembered by anything inside them. Not erased histories, unreadable ones. Now let us extend this idea beyond cosmology. Consider hypothetical regions created in extreme astrophysical events, the core of a neutron star merger, the moment of collapse into a singularity, the inner boundary of a quantum gravity regime. These environments may briefly reach temperatures where no known form of matter can maintain identity. Such states may exist for tiny fractions of a second, but during that time, nothing inside can encode information about itself. When the event ends, only indirect effects remain: gravitational waves, particle jets, radiation patterns, fingerprints, but no testimony. This changes how we interpret data. We are not seeing the most extreme states of matter. We are seeing what survives them, and survival is selective. It filters reality. This means our picture of the universe is biased, not by error or ignorance, but by physical survivability. We know what can leave traces. We do not know what happens where traces cannot exist. And this ignorance is fundamental, not temporary. not technological, built into the structure of reality itself. So when physics speaks of ultimate limits, we must be careful what kind of limit we mean. There are limits of energy, limits of density, limits of temperature, but there are also limits of recordability, and these are often stricter. A phenomenon that cannot be recorded cannot enter science directly. It can only be inferred from absence, from imbalance, from asymmetry, from what did not happen as much as from what did. This brings us to a haunting possibility. There may be entire classes of physical phenomena that shape the universe but never appear in our equations explicitly because they leave no persistent marks. They influence, but do not announce themselves, like heat so intense that it destroys its own footprints. This does not mean such phenomena are unimportant. On the contrary, they may be essential to the universe's evolution. They may govern transitions between eras. They may define why certain structures exist at all, but they do so silently, without witnesses, without archives. And now we arrive at an unsettling question. If the most extreme states of reality cannot be observed even in principle, then how much of the universe will always remain unknown? Not because we failed, but because knowing was never allowed. This does not make science meaningless. It gives it humility. Science describes the reachable, the survivable, the recordable. It maps the shoreline of an ocean. It can never fully enter, and yet this shoreline is vast. Within it lie stars, planets, life, and consciousness. Within it, temperature becomes gentle enough to allow memory, and memory allows understanding. Which brings us to the next layer of this story. If temperature filters reality by deciding what can exist and what can be known, then what role does time play when heat approaches its extremes? Because temperature and time are more deeply connected than they first appear, and that connection is where we go next. Heat and the arrow of time. Why extreme temperature erases the past up to this moment. We have spoken about temperature as a force that reshapes matter. Something that melts, breaks, and simplifies, but now we must look at temperature from a different angle, not as destruction, but as something that quietly governs time itself. In everyday life, time feels obvious. It moves forward. Memories accumulate. Causes precede effects. A glass falls and shatters. It never reassembles itself. Ice melts in a warm room. It does not refreeze spontaneously. We call this direction the arrow of time, and for a long time, it seemed mysterious, because the fundamental laws of physics, at the smallest scales, do not care about direction. They work just as well forward as backward. So, why does time have a preferred direction in the real universe? The answer, quietly, is temperature. More precisely, entropy. Entropy is often described as disorder, but that description is misleading. Entropy is better understood as the number of possible microscopic states that correspond to the same macroscopic appearance. High entropy means many possible internal arrangements. Low entropy means very few, and temperature is deeply tied to this concept. Higher temperature generally allows more microscopic motion, more rearrangements, more possible states. Lower temperature restricts motion and reduces possibilities. The arrow of time points in the direction of increasing entropy, not because time wants to move forward, but because entropy almost always increases in large systems, and temperature is the gatekeeper. Now consider this carefully. Extremely high temperatures. Entropy is already near its maximum. Everything is moving violently. All arrangements are allowed. No configuration is special. In such a state, there is no meaningful before or after. Why? Because nothing persists. No stable patterns, no memories, no records. Time may exist mathematically, but it leaves no trace. The past cannot be distinguished from the present. History dissolves. This is a critical insight. Sufficiently high temperatures. The arrow of time becomes blurred, not because time reverses, but because nothing can record its passage. Without records, time has no texture. No narrative, only flux. This brings us back to the early universe. In its earliest moments, the temperature was unimaginably high. Entropy was enormous, but evenly distributed. There were no gradients, no structures, no memories from the inside, if such a thing were possible. The universe would not feel like a story unfolding that it would feel, like an eternal present only when cooling. Began did entropy gradients appear, differences emerged, energy began to flow from hot regions to cooler ones, and flow creates direction, flow creates time. This means something profound. The arrow of time did not always exist in the way we experience it now. It emerged as the universe cooled. Time, as a lived phenomenon, is a product of temperature falling below certain thresholds. At lower temperatures, structures can persist, atoms form, molecules survive, crystals grow, memory becomes possible, and with memory, the distinction between past and present becomes meaningful. Time gains structure. Now consider the opposite extreme again. If temperature rises high enough, structures dissolve, memory carriers are destroyed. Clocks cannot tick because nothing remains stable enough to count cycles. At that point, the arrow of time does not reverse. It disappears, not because time stops, but because it becomes unobservable from within. This leads to a subtle but important conclusion. Time, like temperature, is not absolute in experience. It depends on conditions, on stability, on persistence, on the ability to record change. Where heat erases stability, time loses meaning. This helps explain why certain cosmic events are so difficult to describe. The moment of singularity formation, the interior of black holes, the Planck era of the universe. These are not just regions of extreme gravity or energy. They are regions where time itself may lose direction, where before and after cannot be cleanly separated. Our equations struggle here not only because the math is hard, but because our intuition about time no longer applies. Now let us turn this idea inward. To ourselves. Human consciousness is deeply tied to time. We remember the past. We anticipate the future. We experience the present as a moving edge between the two, but this experience depends on temperature too. Neural activity requires stable chemical gradients. Reliable molecular interactions raise the temperature of the brain even slightly, and cognition collapses, memory fails. Perception fragments. At higher temperatures, life ends, and with it, the subjective experience of time. This is not coincidence. Consciousness exists only within a narrow thermal window. Too cold, and processes freeze. Too hot, and structure dissolves. Time, as experienced, exists only in between. This gives temperature a new role, not just as a physical quantity, but as a filter of experience. It decides whether time can be felt, remembered, or understood. Now imagine hypothetical forms of existence very different from ours. Could there be observers at much higher temperatures than we can survive? Perhaps, but even they would face the same constraint. To observe time, they would need memory. To have memory, they would need stability, and stability imposes thermal limits and matter the substrate. This logic remains. Thus, there is a deep connection between temperature, time, and existence. Extreme heat does not merely destroy matter. It destroys history. It erases the conditions under which events can be ordered, remembered, and given meaning. And now we reach another quiet threshold. If extreme temperature erases the arrow of time, and if cooling creates it, then what happens at the ultimate future of the universe? When temperatures fall again toward absolute zero, does time fade once more? Does history slow, or stretch, or dissolve differently? That question opens a completely different horizon. Point 1, not of heat, but of cold. And that is where our journey continues next. When the universe grows cold, the slow fading of time. So far, we have followed temperature upward, toward heat so extreme that matter dissolves, memory fails, and time itself loses direction. Now, we turn around, not abruptly, not dramatically, slowly, toward cold. Cold is often imagined as emptiness. As inactivity, as nothing happening, but in the universe, cold is not absence. It is exhaustion. It is what remains after. Everything that could happen already has. Temperature decreases when energy spreads out, when differences disappear. Heat flows from hot regions to colder ones until no gradients remain, and gradients are what drive change. Without them, Nothing moves with purpose, nothing evolves, nothing remembers. This brings us to one of the most unsettling ideas in cosmology, the heat death of the universe. A future state where temperature differences vanish, not because everything freezes instantly, but because everything slowly runs out of ways to change. In such a universe, stars burn out, galaxies drift apart as expansion accelerates, black holes evaporate over unimaginable spans of time, matter decays, radiation thins. Eventually, everything approaches the same temperature. A temperature just above absolute zero. Cold, but uniform. At first glance, this may sound peaceful, quiet, stable, but stability here is not order. It is stagnation. Remember the arrow of time. Time flows where entropy increases, where differences exist, where energy can move from one place to another. In a perfectly uniform universe, entropy is already maximized. There is nowhere else to go. No direction left for time to point toward. This raises a profound question. Does time end when the universe becomes cold? Or does it simply lose all meaning? Clocks may still tick mathematically, but tick toward what? Without change, each moment becomes indistinguishable from the next. The future looks exactly like that present, which looks exactly like that past. Time becomes flat. This is not speculation alone. Our best physical models suggest that in a universe approaching thermal equilibrium, the rate of meaningful events drops towards zero. Processes still occur, but so rarely that they lose narrative significance. A proton decay once every unimaginable number of years. A random quantum fluctuation here and there, but no sustained structure. No evolving systems. No observers, and here we encounter asymmetry with extreme heat at very high temperatures. Time loses meaning because nothing can persist. At very low temperatures, time loses meaning because nothing changes. Point two extremes, opposite conditions, same result. This symmetry is unsettling. It suggests that time, as experienced, exists only in a narrow thermal band between chaos and exhaustion, between melting and freezing. We live inside that band. Consider what this means for existence. Life requires energy gradients. Stars require nuclear fuel. Chemistry requires motion. All of these are temporary gifts of a universe that is cooling but not yet cold. We exist in a brief thermal window. A moment between extremes. Now imagine the far future again. Trillions upon trillions of years pass, not in any dramatic way, but quietly. Expansion stretches space faster than structures can form. Isolated particles drift alone in vast darkness. Temperature differences are gone. Energy is evenly spread across an enormous volume. Nothing remains that could serve as an observer, not because it was destroyed violently, but because it faded with no fuel to sustain itself. This raises an even deeper question. If no observers remain, does time still exist? Or does it become a purely abstract parameter with no physical relevance? Physics allows time to continue mathematically, but experience does not, and without experience, time becomes indistinguishable from non-existence. This is not nihilism. It is a statement about conditions. Time is not a substance. It is a relation between events. When events disappear, time loses its anchor. Some theories suggest that quantum fluctuations could still occur even in a cold universe. Tiny, rare deviations from equilibrium, but these are not enough to rebuild complexity. They are sparks in an ocean without oxygen, fleeting, isolated, unremembered. Others speculate about cycles, universes reborn, new expansions, fresh gradients emerging. But even in these ideas, the cold phase plays a role. It is a reset. A silence before something else begins. Or perhaps not. Perhaps the cold is final. An asymptotic end without drama. No explosion, no collapse, just thinning and thinning and thinning. And here, temperature once again reveals its deeper role. It is not merely a measure of heat. It is a clock. A cosmic clock that ticks as energy spreads and gradients flatten. The lower the temperature, the slower the universe's story moves, until finally, there is no story left to tell. But notice, Something important that we are still here discussing this. Future, which means we are not there yet. The universe is still warm enough for thought, still structured enough for memory, still dynamic enough for curiosity. This makes the present extraordinary, not eternal. Not privileged, but rare. A brief thermal moment where time flows, observers exist, and questions can be asked. And this leads us to the final layer of our exploration. If temperature governs the existence of observers, the direction of time, and the fate of the universe, then what is temperature at the most fundamental level? Is it truly a limit, or merely a shadow of something deeper? That question is where our journey ends. Or perhaps where it truly begins. The final question, why temperature was never the limit. We began this journey with a simple question. How hot can the universe become? It sounded like a problem of numbers, degrees, scales, records, but step by step, that question changed quietly. Almost unnoticed. We learned that temperature is not just heat. It is motion. It is permission. It is destruction and creation measured in the same units. At low temperatures, structure survives. At high temperatures, structure dissolves, and in between, everything meaningful happens. We chased extremes, from laboratory plasmas to stellar cores, from neutron stars to quasars, from the early universe to hypothetical limits set by theory. Each time we thought we were approaching the end, the meaning of the question shifted again. We discovered that temperature cannot be separated from observation, from time, from gravity, from motion. Point 2. Observers can disagree about heat and both be correct. An accelerating observer can feel warmth where another feels vacuum. Temperature is not written into matter alone. It emerges from relationships. Then we crossed a deeper threshold. We realized that beyond certain temperatures, observers cannot exist, not because they are destroyed violently, but because stability itself becomes impossible. No memory, no clocks, no persistence. Reality may still unfold, but without witnesses, and without witnesses, measurement becomes meaningless. We then followed temperature in the opposite direction, toward cold, toward a future where energy spreads thin, differences vanish, and change slows to nothing. A universe not frozen in time, but exhausted of events, where time still exists mathematically, but nothing remains to experience. At point 2. Extremes, heat that erases history, cold that erases the future, same silence. And here, at the end of the path, we can finally see what temperature truly is. It is not a fundamental limit. It is a filter. A condition that decides which realities can exist and which cannot, which structures persist, which observers arise, which histories can be written. There is no ultimate maximum temperature that defines the universe. There is only a boundary beyond which questions lose meaning, not because answers do not exist, but because nothing can remain to ask. This reframes everything. The most important fact about temperature is not how high or low it can go. It is that we exist at all, that the universe cooled just enough, but not too much, that gradients formed, stars ignited, chemistry unfolded, that memory became possible, that consciousness emerged in a narrow thermal corridor between chaos and exhaustion. We are not spectators outside the universe. We are consequences of its temperature history. The universe did not need to allow observers. It simply followed its laws. Cooling was inevitable, and in that cooling, brief windows of complexity opened. We live inside one of them. This does not mean the universe was designed for us. It means that we are temporary expressions of a process that does not care whether it is watched. We are not the goal. We are a phase, and yet that does not make this moment insignificant. On the contrary, it makes it rare across all possible temperatures, across all epochs, across all scales. There are only brief intervals where questions can be asked. We exist inside one of those intervals right now. Someday, the universe will grow too cold for thought. Or perhaps, in distant regions, it once was too hot for memory. Either way, most of reality is silent, unrecorded, unexperienced, and yet, for a moment, there is warmth, not the warmth of stars, but the warmth of understanding, the ability to connect ideas, to trace causes, to imagine futures. This, too, is a product of temperature d'Urso when we ask how hot the universe can be. The quiet answer is this: hot enough to erase itself from memory cold, enough to erase the future, and balanced just long enough to let us exist. Between those two silences, temperature was never the limit. We were, and for a brief moment in cosmic time, that was enough.